The universe stretches in all directions, mostly empty, mostly quiet. Between the nearer stars lie distances so vast that light itself takes years to cross them. In these cosmic gulfs, where no planetary warmth reaches and no stellar wind disturbs the vacuum, ancient objects drift alone. They are the wanderers' fragments of distant worlds, cast into the darkness long before Earth's continents took their current shape, before the first life stirred in primordial oceans, before the moon settled into its familiar orbital dance. These interstellar visitors move through space at speeds that would seem impossible to earthbound observers, yet in the scale of galactic distance, they crawl with geological patience. A typical wanderer might take 50,000 years to cross from one edge of our solar system to the other, moving at 20 kilometers per second through the absolute cold. To put this in perspective, if such an object had begun its journey across our solar system when the last ice age ended on Earth, it would only now be approaching the orbit of Neptune. The mathematics of their motion follow Newton's laws with perfect precision, yet their origins remain shrouded in mystery deeper than any earthly archaeological riddle. Only the occasional gravitational tug from a passing star system alters their trajectory, bending their paths in curves so gradual that entire civilizations could rise and fall between one course correction and the next. These gravitational encounters happen perhaps once every few million years for a typical wanderer, creating subtle changes in velocity that accumulate over cosmic time. The wanderer feels no sensation of acceleration, experiences no awareness of the stellar encounter that has forever changed its destiny. It simply continues, following its new trajectory with the same indifferent persistence it maintained along the old one. Consider the profound silence that accompanies these objects on their journeys. In the vacuum between stars, no sound travels, no wind carries dust, no weather patterns shift and change. The wanderers exist in a realm of absolute acoustic stillness, where the only forces at work are gravity and the faint pressure of starlight. Here, silence takes on an almost physical quality, a presence so complete that it becomes difficult for human minds to comprehend. Even the most isolated places on Earth, the depth of ocean trenches, the heart of Antarctica's ice sheets pulse with seismic vibrations and thermal currents. The wanderers know no such disturbances. Temperature in these interstellar spaces hovers near absolute zero, negative 270 degrees Celsius, cold enough to freeze nitrogen solid, cold enough to make even helium condense into liquid droplets on their surfaces. This cold exceeds anything naturally occurring on Earth by hundreds of degrees. It is the cold of cosmic background radiation, the faint afterglow of the Big Bang itself, barely warming the universe above the theoretical minimum temperature possible. In this cold, molecular motion nearly ceases. Chemical reactions become impossible. Time itself seems to slow to a whisper. The objects themselves appear unremarkable by cosmic standards, chunks of rock and ice, perhaps a few hundred meters across, bearing the chemical signatures of stellar nurseries that exploded into supernova millions of years ago. Their surfaces show the pitted scars of micrometeorite impacts accumulated over eons of travel, each tiny crater a timestamp marking another million years of journey through the galactic void. Yet they carry with them something profound, the geological memory of worlds that no longer exist, preserved in crystalline structures that have remained unchanged since the early epochs of galactic formation. Some wanderers consist primarily of rock fragments of the inner regions of their birth planetary systems, ejected during violent gravitational encounters with massive planets or during the death throes of their parent stars. Others contain significant amounts of water ice, methane, and ammonia refugees from the outer reaches of distant solar systems, carrying within their frozen hearts the chemical signature of primordial nebular material. Still others represent exotic compositions entirely unknown in our solar system. Assemblages of minerals that formed under conditions of temperature and pressure that exist nowhere in our cosmic neighborhood. Their surfaces show no weathering from atmosphere or water, no erosion from biological processes, no signs of the countless forces that constantly reshape the surfaces of planets. They are time capsules, frozen monuments to planetary systems that formed and died before our sun was even a distant possibility in a collapsing molecular cloud. The oldest among them may have begun their journeys when the Milky Way galaxy was half its current age, carrying chemical information from stellar generations so ancient that their very elements represent different epochs in cosmic nucleosynthesis. Each wanderer follows its own unique trajectory through the galaxy, a path determined by the gravitational circumstances of its ejection from its home system billions of years ago. The initial conditions of this ejection, the mass and orbital characteristics of the ejecting planet, the precise timing of the gravitational encounter, the orientation of the planetary system relative to galactic coordinates, all combine to create a trajectory as unique as a fingerprint. Some travel in nearly straight lines, barely deflected by stellar encounters, maintaining courses that will carry them clear across the galaxy's disk in 1 billion years. Others follow complex orbital patterns around the galactic center, their paths looping through spiral arms and stellar neighborhoods in cycles that span hundreds of millions of years. The galaxy itself rotates beneath them, stars and planetary systems shifting positions like slow dancers in a cosmic ballroom, while the wanderers maintain their ancient courses with stubborn persistence. Star formation regions bloom and fade. Massive stars exhaust their nuclear fuel and explode as supernovae. New planetary systems condense from the enriched gas and dust. Through all these changes, the wanderers continue their patient journeys, older than most of the stars they pass, carrying within their silent hearts the chemical memories of cosmic epochs long forgotten. Astronomers estimate that at any given moment, several of these interstellar objects are passing through our solar system. The calculation appears straightforward, yet produces results that stagger the imagination if space contained just one interstellar object per cubic astronomical unit, a volume roughly equivalent to a sphere with Earth's orbital radius, then dozens would be crossing our solar system's boundaries at this very moment. Current theoretical models suggest the density may be even higher, with thousands of wanderers drifting undetected through the space between planets at any given time. Most remain invisible to human observation, too small and dark to reflect enough sunlight for detection by even our most sensitive instruments. They slip past unnoticed, like distant ships passing in the night, their presence known only through the subtle mathematical perturbations they create in the orbits of more familiar bodies. These gravitational signatures require years of precise measurement to detect, and even then remain ambiguous, easily confused with observational uncertainties or previously unknown asteroids from our own solar system's outer reaches. Only occasionally does one pass close enough to our instruments to reveal its foreign nature, its spectral signature announcing that it belongs to no family of objects born in our solar neighborhood. These rare discoveries represent triumphs for human patience and technological precision, the culmination of decades spent developing increasingly sensitive detection methods. Astronomers must sift through millions of observations, tracking the movements of countless points of light, searching for the telltale signs of hyperbolic orbits that betray an object's extrasolar origin. 4.5 billion years ago, In stellar neighborhoods whose names no human language will ever speak, planetary systems undergo their final architectural arrangements. Young gas giants, still warm from their formation, migrate inward and outward through debris-filled orbital zones, their immense gravitational fields reshaping the distribution of smaller bodies with casual violence. The process unfolds over millions of years, yet from the perspective of individual planetesimals, the building blocks of future planets, each gravitational encounter lasts mere hours. These encounters follow predictable mathematical patterns, yet their outcomes depend on initial conditions so precisely balanced that tiny variations produce vastly different results. A planetesimal approaching a gas giant at one angle becomes captured in a stable orbit, eventually accreting into a moon. The same object, approaching with its trajectory shifted by mere kilometers per second, receives a gravitational boost that flings it beyond the reach of its parent star's influence, transforming it from a potential moon into an interstellar wanderer. The ejection itself represents a moment of cosmic irony. The same gravitational interactions that build planetary systems also tear them apart, scattering their raw materials across the galaxy. The gas giants that will eventually nurture stable orbital zones around their parent stars first spend millions of years acting as gravitational catapults, launching countless smaller objects into the void. Each ejection removes potential building material for future planets, yet the process appears essential to the formation of stable planetary architectures. During this epoch of heavy bombardment and orbital rearrangement, entire categories of objects receive their eviction notices from gravitational landlords they will never see again. Rocky planetesimals from the inner system, their surfaces already scarred by countless collisions with similar bodies, find themselves accelerated beyond escape velocity by close encounters with migrating giants, icy objects from the outer reaches, rich in water and organic compounds that might have seeded life on inner planets. Instead begin journeys that will carry them through interstellar space for billions of years. The mathematics governing these ejections reveal a curious property. Most objects launched from planetary systems carry with them velocities that closely match the orbital speed of their parent stars around the galactic center. This means that newly ejected wanderers initially travel through space on trajectories roughly parallel to their birth stars, like cosmic motorcycles maintaining formation on a galactic highway. Only over millions of years do differential gravitational forces from other stars gradually disperse them into truly random trajectories. Consider the perspective of a single rocky fragment during its moment of ejection. For billions of years, this object has known only the gravitational embrace of its parent star, orbiting in predictable cycles that bring regular variations in temperature and illumination. Its surface bears the chemical signatures of countless impacts with similar objects, the molecular traces of a planetary formation process that has continued for millions of years. Then, in a matter of hours, a close encounter with a massive planet accelerates it beyond escape velocity. The transition from bound to unbound occurs at a precise mathematical boundary, the moment when the object's kinetic energy equals its gravitational potential energy relative to its parent star. Before this moment, it remains forever trapped in orbital dance. After this moment, it becomes a citizen of the galaxy itself, free to wander among stellar neighborhoods it has never seen. The boundary itself exists as a mathematical abstraction, yet its crossing represents one of the most fundamental transitions possible in celestial mechanics. Some ejected objects carry with them more than just rock and ice. complex organic molecules, synthesized in the reducing atmospheres of gas giant moons or delivered by earlier generations of interstellar visitors, become passengers on these cosmic journeys. Amino acids, nucleotide bases, and other chemical precursors to life begin interstellar voyages that will last longer than the total evolutionary history of complex life on Earth. These molecular hitchhikers travel in deep freeze, their chemical bonds preserved in crystalline matrices that maintain their structure across geological time. The ejection process itself demonstrates the fundamental asymmetry between creation and destruction in cosmic systems. Building a planet requires millions of coordinated accretion events, each one adding mass in precisely the right location and velocity vector to contribute to a stable, spherical body. Ejecting potential planetary material requires only a single gravitational encounter lasting a few hours. The universe, it seems, finds destruction far easier than construction, yet both processes operate with equal mathematical precision. Theoretical models suggest that every planetary system loses a significant fraction of its initial solid material during these early phases of gravitational reorganization. The percentage varies depending on the masses and orbital characteristics of the gas giants involved, but estimates range from 10 to 50% of all solid matter being ejected entirely from the system. This means that the wanderers drifting through interstellar space may actually outnumber the objects that successfully assembled into planets, moons, and asteroid belts. The timing of these ejections creates a curious cosmic phenomenon. Waves of interstellar objects launched from multiple stellar systems during the same general epoch in galactic history, young star clusters containing dozens or hundreds of newly formed stellar systems, simultaneously undergo their periods of planetary architectural rearrangement. The result is a temporally correlated burst of wanderers entering the galactic medium, all sharing similar ages despite originating from different stellar neighborhoods. These ejection epochs can be dated through careful analysis of stellar formation rates in different regions of the galaxy. Periods of intensive star formation, triggered by galactic spiral arm passages or collisions with satellite galaxies, produce corresponding increases in the population of interstellar objects several million years later. The delay corresponds to the time required for newly formed planetary systems to complete their gravitational reorganization and begin launching their excess material into interstellar space. Current observations suggest that our galaxy produces approximately one interstellar object per star system during the planetary formation epoch. With over 100 billion stars in the Milky Way, this implies a total population of wanderers numbering in the hundreds of billions of vast, invisible diaspora of objects carrying the chemical and geological signatures of their birth worlds across the galaxy. Only a tiny fraction will ever be detected by human instruments, yet they represent one of the most numerous categories of objects in galactic space. The process continues today in younger stellar systems, where gas giants still migrate through debris-rich orbital zones, and planetesimals still experience the gravitational encounters that will determine their cosmic fate. Somewhere in the galaxy at this moment, another rocky fragment receives the acceleration that will transform it from a potential component of an alien world into a wanderer destined for interstellar space. The transformation occurs without ceremony, marked only by the silent crossing of a mathematical boundary that separates the bound from the unbound, the local from the cosmic, the temporary from the eternal. The wanderer moves through darkness so complete that human language lacks adequate words to describe it. This is not the darkness of a moonless night, where starlight still provides faint illumination, nor the darkness of deep ocean trenches, where bioluminescent creatures create their own light. This is the darkness between stars, where the nearest light sources lie trillions of kilometers away, their photons so widely scattered that a human eye would detect fewer than a dozen per second. Even with perfect dark adaptation, temperature here stabilizes at 2.7 Kelvin above absolute zero, maintained not by any nearby heat source, but by the cosmic microwave background radiation that permeates all of space. This represents the faint afterglow of the Big Bang itself, cooled and redshifted by 13.8 billion years of cosmic expansion. The Wanderer's surface exists in thermal equilibrium with this primordial radiation, neither gaining nor losing heat, suspended in a state of perfect energetic balance that could theoretically persist forever. The object itself measures perhaps 300 meters across its longest axis, roughly the size of 3 city blocks placed end to end. Yet its mass contains more material than humans have ever extracted from Earth's crust in all of recorded history. Its composition reflects the chemical signature of its birth system. Silicon and iron dominate the rocky matrix, while trace amounts of more exotic elements tell stories of the stellar nucleosynthesis processes that created them. Aluminum-26, with its half-life of 700,000 years, has long since decayed away, taking with it the radioactive heat that once warmed the object's interior during its first million years of existence. Surface features reveal the accumulated damage of 4 billion years travelling through interstellar space. Micrometeorite impacts have sandblasted the leading hemisphere, creating a layer of fine regolith that covers the original crystalline structure like cosmic dust. Each impact crater, from microscopic pits to meter-wide depressions, represents an encounter with another piece of interstellar debris travelling at relative velocities measured in tens of kilometers per second. The mathematics of these collisions produces a characteristic crater-size distribution that astronomers can use to estimate the object's exposure age to the interstellar medium. Cosmic ray bombardment has altered the surface chemistry in ways that would fascinate nuclear physicists. High-energy protons and heavier atomic nuclei, accelerated by supernova explosions and other violent astrophysical processes, strike the Wanderer's surface with enough energy to split atomic nuclei and create entirely new isotopes. Over millions of years, this cosmic ray spallation process has created a thin surface layer enriched in rare isotopes that exist nowhere else in nature. Helium-3, produced when cosmic ray protons strike lithium nuclei, accumulates in the surface regolith at concentrations far exceeding anything found on Earth. The Wanderer's rotation period has evolved over cosmic time through a complex interplay of forces that operate on timescales measured in geological epochs. Initially, it may have tumbled chaotically, spinning at rates determined by the violence of its ejection from its parent planetary system. Over millions of years, however, the subtle asymmetric pressure of starlight gradually damps this chaotic motion through a process called Yorp effect, named after the 4 astronomers who first described it mathematically. The object slowly settles into a more stable rotation state, typically spinning about its axis of maximum moment of inertia. Currently, the Wanderer completes one rotation approximately every 18 hours, a period that has remained stable for the past 100 million years. This rotation creates the closest thing to weather that the object experiences as different hemispheres alternately face the direction of motion through space. They encounter slightly different fluxes of cosmic rays and interstellar particles. The resulting variations in surface temperature amount to mere thousandths of a degree, yet they represent the only temporal changes in an otherwise perfectly static environment. Navigation through interstellar space follows principles that would seem familiar to ancient mariners, yet the reference points exist on scales that dwarf terrestrial navigation. The wanderer's trajectory can be traced backward through galactic coordinates, accounting for the differential rotation of spiral arms and the gravitational perturbations of massive stellar objects encountered during its journey. These calculations suggest it originated in a stellar association that no longer exists as a coherent structure, its member stars having dispersed across hundreds of light years during the 40 million years since the wanderer's ejection. The object's current velocity of 23 kilometers per second relative to nearby stars places it in the middle range of observed interstellar object speeds. This velocity has changed by less than 1% during its entire interstellar journey, demonstrating the profound emptiness of space between stellar systems. Occasional encounters with interstellar gas clouds produce drag forces measured in piconewtons, forces so small they would barely deflect a soap bubble in Earth's atmosphere, yet accumulating over millions of years to produce measurable changes in trajectory. Magnetic field interactions create the most exotic physical phenomena experienced during the wanderer's journey. The object carries within its crystalline structure a weak magnetic field, frozen into its metallic components during its formation 4 billion years ago. As it moves through the galaxy's magnetic field at 23 kilometers per second, it generates electric fields measured in microvolts per meter. These fields, while incredibly weak, are sufficient to accelerate any free electrons or ions present on the surface, creating microscopic aurora effects invisible to human observation but detectable by sensitive instruments. The wanderer encounters other objects perhaps once every few million years, typically collisions with interstellar dust grains traveling at similar velocities. These encounters occur with such rarity that each represents a statistically significant event. The collision mechanics follow well-understood principles of impact physics, yet the outcomes depend critically on the detailed internal structure of both objects. Most encounters result in the mutual vaporization of both participants, creating expanding clouds of plasma that dissipate into the interstellar medium within hours. Gravitational interactions with passing stars occur on even longer timescales, perhaps once every 10 to 50 million years depending on the local stellar density. These encounters rarely involve close approaches. Typical distances exceed several thousand astronomical units. Yet, they produce measurable changes in the wanderer's trajectory. Each stellar encounter acts like a weak gravitational lens, bending the object's path by small angles that accumulate over cosmic time to produce significant course changes. The wanderer carries no instruments to record its journey, no sensors to measure the cosmic phenomena it encounters, no memory devices to store the data of its passage through space. Yet its very existence provides information about the galaxy's structure and evolution that cannot be obtained through any other means. Its composition tells stories about stellar nuclear synthesis in its birth system. Its crater record provides a census of the interstellar dust population. Its trajectory traces the gravitational architecture of stellar neighborhoods it has crossed during its billion-year journey. Radio telescopes occasionally detect the faint electromagnetic emissions created when cosmic rays strike the wanderer's surface, producing brief bursts of radiation that last microseconds and carry total energies measured in joules. These signals, weaker than the electromagnetic noise generated by a digital wristwatch, nevertheless carry information about cosmic ray flux densities and magnetic field configurations in regions of space that no spacecraft will visit for millions of years. The wanderer broadcasts its presence across the galaxy through these whisper-faint transmissions, though no receiver sensitive enough to detect them has yet been constructed by human technology. Time itself flows differently for an object existing in such profound isolation from external reference frames, without seasons, without day-night cycles, without any periodic phenomena to mark its passage. The wanderer exists in a state approaching temporal suspension. Changes occur so slowly that millions of years pass without producing any alteration visible to hypothetical observers. It persists in a state of geological meditation, carrying its ancient chemical memories through spaces so vast and time so long that its journey begins to resemble a form of cosmic consciousness, patient beyond human comprehension. On October 19th, 2017, astronomers at the Haleakala Observatory in Hawaii notice an anomaly in their routine survey data. A faint point of light moves against the background stars with motion, too rapid for any asteroid native to our solar system. Initial calculations suggest an object following a hyperbolic trajectory, the mathematical signature of something unbound by the sun's gravitational influence. Within days, observatories around the world pivot their instruments toward this visitor, beginning humanity's first detailed study of a confirmed interstellar object. The object receives the designation unattached, Oumuamua, using a new nomenclature system hastily created to categorize interstellar visitors. The name comes from Hawaiian words meaning scout or messenger from afar, chosen to honor both the observatory that discovered it and the Pacific traditions of navigation by distant landmarks. Yet as observations accumulate, Oumuamua proves to be a messenger bearing news stranger than anyone anticipated. Its trajectory through the solar system follows a precise hyperbolic arc, exactly as expected for an object with an interstellar origin. The mathematics appear straightforward. Gravitational attraction from the sun bends the visitor's path into a sharp curve, accelerating it to speeds exceeding escape velocity as it approaches perihelion. Computer models predict its position with extraordinary accuracy during the first weeks of observation, confirming that celestial mechanics operates with the same precision for interstellar visitors as for familiar solar system objects. Then the predictions begin to fail. High-precision astrometric measurements reveal that Oumuamua is accelerating away from the sun slightly faster than gravity alone can explain. The discrepancy measures only a few millimeters per second squared, a force so gentle it would barely register on the most sensitive scales, yet it accumulates over months to produce positional errors of thousands of kilometers in the predicted trajectory. The unexpected acceleration immediately sparks intense scientific debate. Comets routinely exhibit similar non-gravitational forces when solar heating vaporizes their icy surfaces, creating jets of gas that act like tiny rocket engines. But Oumuamua shows no signs of outgassing, no visible coma, no spectroscopic evidence of water vapor or other volatiles, no brightening as it approaches the sun. Its surface appears as inert as a chunk of metallic rock, yet something invisible is pushing it away from the solar system. Proposed explanations multiply as rapidly as new observations arrive. Perhaps Oumuamua possesses an unusual composition that allows it to outgas materials invisible to optical telescopes. Perhaps cosmic ray bombardment during its interstellar journey has altered its surface chemistry in ways that create unexpected thermal properties. Perhaps it represents a new category of object entirely unknown to solar system astronomy. The most exotic hypothesis suggests that radiation pressure from sunlight itself provides the mysterious acceleration for this mechanism to work. Oumuamua would need to possess an extremely unusual shape, perhaps a thin, flat sheet, only a few meters thick but hundreds of meters across, like a cosmic sail optimized to catch photons instead of wind. Such a geometry would maximize surface area while minimizing mass, allowing the gentle pressure of sunlight to produce measurable acceleration. Shape determination proves challenging because Oumuamua varies dramatically in brightness as it rotates, suggesting an elongated form unlike any asteroid previously observed. Light curve analysis indicates an object at least 10 times longer than it is wide, tumbling end over end with a rotation period of 7.3 hours. Whether this represents a needle-like cigar shape or a flat pancake-like disk remains ambiguous. Both geometries could produce the observed brightness variations. Spectroscopic observations reveal a surface composition that defies easy categorization. The object reflects sunlight with characteristics intermediate between rocky asteroids and metallic meteorites, yet matches neither category precisely. Its color appears distinctly reddish, suggesting either iron oxide weathering or organic compounds created through cosmic ray bombardment during its interstellar journey. No absorption lines indicate the presence of water ice or other volatiles that might explain the non-gravitational acceleration. The mystery deepens when astronomers calculate Oumuamua's trajectory backward through time, attempting to trace its path to its system of origin. The backward integration suggests it has been traveling through interstellar space for millions of years, yet its trajectory does not clearly point toward any nearby star system. Either it originated from a very distant stellar neighborhood, or gravitational encounters during its journey have erased the signature of its birth system. Current velocity measurements indicate Oumuamua approached our solar system from the direction of the constellation Lyra, moving at approximately 26 kilometers per second relative to nearby stars. This speed places it within the expected range for objects ejected from planetary systems during their formation epochs, yet provides few clues about its specific origin. Millions of stars lie in the general direction of its approach, any of which could have hosted the planetary system that originally expelled this wanderer. The object's size estimates vary depending on assumptions about its shape and surface reflectivity, but most calculations suggest a maximum dimension between 100 and 1,000 meters. If it possesses the elongated geometry indicated by its light curve, Oumuamua might measure 800 meters long and only 80 meters wide dimensions that would make it one of the most extreme shapes ever observed among small solar system bodies. As Oumuamua races toward the outer solar system, carrying its secrets beyond the reach of detailed observation, it leaves behind more questions than answers. Its brief passage transforms humanity's understanding of interstellar objects from theoretical possibility to observational reality. Yet its anomalous behavior suggests that the first confirmed visitor from another star system possesses properties unlike anything in our cosmic neighborhood. The acceleration mystery remains unsolved despite months of intensive study by dozens of research teams worldwide. Each proposed explanation faces observational challenges or requires assumptions about Oumuamua's properties that stretch the boundaries of plausibility. Perhaps the visitor represents a category of object common in other stellar systems but entirely absent from our own, carrying with it physical properties shaped by environmental conditions that exist nowhere in our solar neighborhood. Radio telescope searches detect no artificial signals emanating from the object. Yet the very fact that such searches are conducted reveals how thoroughly Oumuamua has challenged conventional assumptions about interstellar visitors. Its combination of unusual properties, extreme elongation, mysterious acceleration, anomalous composition, forces astronomers to confront the possibility that objects formed in other stellar systems might differ dramatically from familiar solar system bodies. By early 2018, Oumuamua fades beyond detection by even the largest telescopes, carrying its enigmas back into the darkness between stars. Its passage through our solar system lasts less than 2 years, yet provides humanity with the first concrete evidence that space between stars contains wandering objects accessible to direct observation and study. The visitor departs as mysteriously as it arrived, leaving behind a transformed understanding of what might exist in the cosmic gulf between stellar neighborhoods. 3 years after Oumuamua's departure, another faint point of light appears in the routine survey data from the Crimean Astrophysical Observatory. The object moves with the characteristic motion of a comet, yet preliminary orbital calculations suggest something unprecedented, a trajectory that originates from beyond the solar system's gravitational boundary. On August 30th, 2019, astronomers confirm that Comet Tuohy-Borisov represents humanity's second confirmed interstellar visitor, and the first to display the classical behavior expected from such objects. Unlike its mysterious predecessor, Tuohy-Borisov behaves exactly as theory predicts an interstellar comet should behave. As it approaches the Sun, solar heating begins sublimating water ice and other volatiles from its nucleus, creating the characteristic coma and tail that make comets visible from vast distances. Spectroscopic analysis reveals familiar signatures: water vapor, carbon monoxide, and cyanogen, the same molecules that outgas from comets born in our own solar system's outer reaches. The comet's nucleus appears refreshingly ordinary by solar system standards, a dark, irregular chunk of rock and ice measuring approximately 1 kilometer across, spinning with a rotation period of roughly 8 hours. Its surface reflects only 3% of incident sunlight, giving it the coal-black appearance typical of comet nuclei that have spent billions of years exposed to cosmic radiation. No exotic accelerations complicate its trajectory. It follows precisely the hyperbolic path predicted by celestial mechanics. Yet Tuohy-Borisov carries within its icy matrix chemical signatures that tell extraordinary stories about its origin. As the comet approaches, perihelion and outgassing intensifies. Sensitive spectrometers detect subtle variations in isotopic ratios that distinguish its composition from any object native to our solar system. The ratio of carbon-12 to carbon-13 in its carbon monoxide emissions differs measurably from solar system values, providing the first direct evidence of chemical processes that occurred in an alien planetary system. Water molecules evaporating from the comet's nucleus show similarly exotic isotopic signatures. The ratio of deuterium to ordinary hydrogen suggests formation in an environment with different temperature and pressure conditions than those that shaped objects in our solar system's outer regions. These molecular fossils preserve information about the primordial nebula from which the comet condensed billions of years ago, a stellar nursery that may have been enriched by supernovae explosions with different timing and chemical yields than those that influenced our Sun's formation. Detailed analysis of the outgassing patterns reveals additional peculiarities that distinguish Tuohy-Borisov from solar system comets. The rate at which water sublimates from its surface follows a different temperature dependence than expected, suggesting either an unusual surface composition or structural differences in how ice molecules are bound within the nucleus. Perhaps the extreme cold of interstellar space has altered the crystalline structure of water ice in ways that affect its sublimation properties when exposed to solar heating. The comet's approach trajectory can be traced backward with much greater precision than was possible for Oumuamua, thanks to the continuous outgassing that creates measurable non-gravitational forces. These calculations suggest Tuohy-Borisov has been travelling through interstellar space for millions of years, possibly originating from a red dwarf star system located dozens of light-years away. The candidate origin systems include several nearby M-dwarf stars known to host planetary systems, though pinpointing the exact source remains beyond current observational capabilities. As 2I Borisov rounds the Sun and begins its outbound journey, its behavior continues to confound expectations in subtle ways. The comet's brightness varies more dramatically than predicted as different regions of its nucleus rotate into sunlight, suggesting an unusually heterogeneous surface composition. Some areas appear rich in volatile materials that sublime readily when heated, while others seem dominated by more refractory compounds that resist outgassing, even at perihelion distances. High-resolution imaging reveals that the comet's coma possesses an asymmetric structure unlike the roughly spherical envelopes typical of solar system comets. Jets of gas and dust appear concentrated in specific directions, possibly reflecting the influence of subsurface composition variations or structural features inherited from its formation environment. These asymmetries persist throughout the comet's passage, suggesting fundamental differences in internal architecture compared to familiar cometary objects. The comet's dust production provides another window into its alien heritage. Particles ejected from its nucleus during outgassing episodes display size distributions and optical properties that differ subtly but measurably from solar system comet dust. Microscopic analysis of particles captured by spacecraft instruments might reveal mineralogical signatures of formation processes that occurred under different stellar radiation environments or nebular chemistry conditions. Attempts to detect organic molecules in 2I Borisov's coma yield intriguing but ambiguous results. While water, carbon monoxide, and simple cyanogen compounds appear abundant, more complex organic species remain elusive. Either the comet formed in an environment depleted in organic precursors, or the harsh conditions of interstellar travel have destroyed more fragile molecular structures through cosmic ray bombardment and photodissociation by starlight. The visitor's orbital eccentricity exceeds 3.3, placing it decisively in the hyperbolic category that confirms its interstellar origin. Yet this eccentricity is only barely sufficient to escape the solar system, suggesting that 2I Borisov may have originated from a stellar system with orbital velocities similar to those around our Sun. Objects ejected from systems orbiting more massive stars would typically carry much higher excess velocities, while those from lower mass stellar systems might not achieve the speeds necessary to reach our solar neighborhood. Radio-astronomical observations detect no unusual electromagnetic emissions from the comet beyond those expected from natural plasma processes in its coma. The sublimating gases create a weak ionosphere around the nucleus that interacts with the solar wind to generate radio waves at predictable frequencies. These emissions provide additional information about the comet's gas production rates and the electromagnetic environment within its coma, yet reveal nothing obviously alien about its physical processes. Photometric monitoring throughout 2I Borisov's passage through the inner solar system confirms that its activity level remains remarkably stable compared to many solar system comets. While most comets display erratic brightness variations caused by evolving surface features and changing sublimation rates, 2I Borisov maintains relatively consistent outgassing throughout its approach and departure. This stability suggests either a more homogeneous internal composition or surface properties that respond predictably to solar heating. As the comet fades into the outer solar system, carrying its chemical secrets back toward interstellar space, it leaves behind a legacy of measurements that transform understanding of planetary formation processes in other stellar systems. Its relatively normal behavior, contrasting sharply with Oumuamua's enigmatic properties, suggests that interstellar space contains a diverse population of objects representing different formation environments and evolutionary histories. The successful observation of 2I Borisov demonstrates that current astronomical techniques can extract detailed compositional and physical information from interstellar visitors, provided they display sufficient activity to become detectable from large distances. Future surveys may discover dozens of similar objects, gradually building a comprehensive picture of how planetary formation processes vary among different stellar environments, and how billions of years of interstellar travel affect the